Hello everyone, I'm Quan-Jun Chen from National Taiwan University. Today my topic is chemical and mechanical pressure-induced photoluminescence tuning via structural evolution and hydrostatic pressure. In traditional, the food analyzer is quite big and it is impossible to carry it with yourself. Therefore, our target is use the NIR PCLD with the smartphone, and some of the broadband NIR light will be absorbed by the food. By comparing the before and the after spectra, we can get some information about the food. My presentation will be divided into 4 parts. The first part is the introduction, second is experimental, and then is results and discussion. Finally, I will give my conclusion about my research. In 1988, Professor Induced's group first gave the research on the gallium arsenide doping with chromium. They discussed the emission spectrum of this material in different temperatures. And in 2014, Professor Pan's group did the research on the persistent luminescent properties of these materials. And in 2021, Professor Liu's group did the research on the solid solution of gallium arsenide doping with scandium into the structure and investigate the luminescent properties. From the previous research, we can realize that they focus on the persistent luminescence. The spectral peak shift mechanism is unexploited, and the emission bandwidth is insufficient. Hence, our approach is to do the PCNIR LED package to evaluate the performance of our phosphor. The cation site substitution is applied to investigate the spectral peak shift mechanism. Finally, mixing with the phosphor of gallium arsenide doping with scandium can extend our bandwidth of emission. Our research goal is synthesis and crystallization of the gallium arsenide doping with different concentration of aluminum. And we also do the LED package for the mixture of our phosphor and the gallium arsenide doping with scandium. Here is the experimental part. First, we weight our precursor based on stoichiometry and transfer them into the motor. Second, we grind the powder for 20 minutes. Third, we put the powder into the crucible and sinter it in the furnace for 5 hours at 1550 degrees in the air. From the XRD result, we can find out that the peak shift to the higher angle due to the lattice shrinkage, which means the aluminum gets into the structure successfully. Besides, when X equals 1.6, the crystal phase change is observed, and with the higher content of aluminum, the main phase becomes aluminum oxide. For the gallium arsenide crystal structure, there are 2 sites for the cation. First is Ga1, which is a tetrahedral site, and the other one is Ga2, which is an octahedral site. As for the aluminum oxide crystal structure, there is only one octahedral site for the cation. To investigate the structure further, the structural refinement is conducted. Here we put the X equals 1.6 demonstration. The refinement result is quite good, and we find out that the doping cation will go into both gallium site and aluminum site. From the refined occupancy and the lattice parameters, we can find out that there is no preferred occupancy for aluminum, and the volume of the lattice is shrinkage due to aluminum doping. From the room temperature PO measurement, we can find out that the spectrum blue shift, and it results from the shrinkage of lattice and enhance the crystal field strength of structure. We also measure the internal quantum efficiency to evaluate the potential of this series of phosphors. We can find out that all samples obtain quite high IQE performance. It is worth noting that we find out when the sample under high pressures, there is a new emission band from extrinsic coupled chromium 3+ pair, and it is from the alpha phase of gallium arsenide when the high pressure is induced. In order to realize the thermal property of the samples, the temperature-dependent photoluminescence is conducted, and we can find out when the temperature increases, the broadband emission dominates due to the thermal occupancy of the 42 state. On the other hand, we also find out when we increase the content of aluminum, the thermal stability is higher. To obtain the information of local structure, the electron spin resonance analysis is conducted. The chromium side of gallium oxide show higher distortion than aluminum oxide. Finally, we fabricate the LED package for the mixture of gallium arsenide doping with scandium and aluminum. From this strategy, we can obtain the ultra-broadband emission with high output power. In conclusion, our research achievement is success of solid solution and broadband to line emission covering from 650 to 950 nanometer, and we also got a high radiant flux and broadband emission spectrum. Thanks for your attention.